Hi everybody and welcome. After watching today's video, your goal is going to be able to solve application problems using exponential and logarithmic functions. So one of the key aspects we're going to see exponential and logarithms applied is to interest and compound interest. So taking a look at that today, this should be a little bit of review, some of the parts, but a little bit of new material in some of the parts as well, looking at some real world examples involving compound interest. So compound interest formula, start there. And then we're going to take each piece of this formula and break it down into what it means. So A is the total amount. So this is what you get paid out. P is your initial investment. This is sometimes called principal. R is the rate, the interest rate, sometimes referred to as APR. N is the number of times it's compounded each year. And then T is the number of years. So this is for a typical calculation where they give you a rate, they give you a number of times that things are compounded. There is a second type of calculation where they are always compounding. So this is continuous compounding. So in this case, we have A equals P times e to the RT power. And in this case, A is the same, P is the same, E is a number. It's approximately equal to 2.7, but it's just a number. And R and T are both the same. So this is just a slightly simplified formula, and it only works when things are compounded continuously. So these are the two things that we have here to start off. So we'll jump into an example. We'll practice plugging things in, and that'll take us to the end of the skill for today. So an initial investment of $1,000, period of 8.5 years, and that's all the information we have so far. So this is P. So our initial investment is what we have here. So $1,000 is what we initially put in, so that is our principal, or P. Here, for years, we have 8.5. So that is going to be T, because T is measured in years. Our rate is R. And then semi-annually. So it might be useful here to break out a table. So annual has an N of 1. Semi-annual has an N of 2. Quarterly has an N of 4. Monthly has an N of 12. We could see daily has an N of 365, and so on. So that's the idea here as we're breaking these down. So semi-annually has an N of 2. In this case, R is 6%, so it's 0.06. Make sure you write it as a decimal, not a percent, and that'll make plugging in quite a bit easier there. So plugging this one into our formula, you have 1,000, 1 plus R over N, and then N times T power. So we can work through this one and basically just punch it all into our calculator, and that's going to determine what we get here. So start off here, if we have 0.06 divided by 2 plus 1, so this will get 1,000, that's 1.03, and then 2 times 8.5 to the 17th power. So we'll do 1.03 to the 17th power, and then multiply that by 1,000. And that should get us an answer of 1,652.84. So that'll bring us to what we're looking at here for compounded semi-annually. We could do the same thing, plug in for the rest of these, but we're going to save a little bit of time with B and C because they're very, very similar. So again, as long as we can define what these R's are, and again, it goes back into that same formula. But I want to practice with D and show this example out because this is continuous, so we're going to be using a different formula. This will be the A equals P-E RT. So principal in this case, still 1,000. E is a number, so we never ever plug in anything for E. Our R is 0.06. Excuse me. And our T is still 8.5. So punch that into the calculator. So it'll be e to the 0.51 power times 1,000. And we'll see that this is $16.55.25. So pretty good in terms of getting a little bit more money out of the bank here with a continuous interest rate. But we're going to see all these, they don't really differ too much from each other. They're all within the same ballpark of where they were. And I wrote this down, I'm sorry, 16.65, not 55. So about $13 more if it is continuous interest. So that's the idea. Basically take it, plug it into your calculator. As long as you're plugging into the formula correctly, everything should work out pretty well for you. But we can work backwards, and this is where the entire unit that we were just doing comes into play for the real-world application. Taking the skills that we have and then applying it to something that might not be quite as straightforward as plugging in. So initial investment here of 1,000, and the amount, we want to see when does it double. So what is the amount that we get actually double to 2,000? So our rate here is 0.06, compounding continuously, so that's going to tell us we're using A equals PERT. So we're going to plug in everything that we know, and then we're going to solve for what we don't know. So $2,000, 1,000 here, our rate of 0.06, and then T is what we don't know. So this is the step where we go through and we solve for T. So we can divide both sides by 1,000, and we're left with 2 is equal to E times 0.06T. And then from here, we can rearrange this as a log. So we can do ln of 2 is equal to 0.06t. And then we can divide both sides by 0.06. And we're left with t is equal to ln of 2 divided by 0.06. Now remember, you can't touch that 2 because it is inside of the ln. So the only thing that we can do from here is actually punch this into our calculator. So the ln of 2 divided by 0.06. And if we do that, we'll get a time of 11.6 years. And that's going to tell us how long it'll take for our money to double. So if you have a 6% interest rate, you compound it all the time, continuously, you're going to see after 11 and a half years, a little bit more than 11 and a half, you'll see that your money will double. So that is what we are looking for in that example. So now we can move forward to our final example here, which is talking about growth and decay. So we can see quantities that grow or decay over time can be modeled with these exponential functions, so we can use these models to predict and solve for unknown values. So in our first one, initially, how many bacteria do we have? Well, our initial value, our initial investment, the P, is equal to 1,000. The growth rate is R, so the R in this function is 0.01. We can also write this as 1%. So decimal versus percent, similar, but just slightly different. And then here, population after 24 hours, well, we're saying, in this case, T, the time is in hours. So we can say that T is equal to 24. So we could do 1,000 times E, 0.01 times 24. So this is, again, just calculator math. Jump over to the calculator. E to the 0.01 times 24. Multiply that by 1,000. And we'll see here 1,271 we'll say about 25. So that's how much bacteria are in the population. Now finally, one example of solving here is when will it reach 8,000? So again, set it equal to 8,000, and then from here we plug in everything else that we already have. We just don't know the time. So when is telling us solve for the time. So what is T? So follow the same steps we did on the back side. Divide both sides by 1,000. We'll get 8 is equal to E to the 0.01T. And another great example of where ln helps us. Rearrange our exponential function as a logarithm. Divide both sides by 0.01. And this ln over 0.01, ln of 8 over 0.01 will give us the final answer. So again, more calculator math, ln of 0.08 divided by ln of 8 divided by 0.01, and we'll get a time of 208 hours. Just remember, time in this case is in hours. So 208 hours, our population will go times 8, go all the way up to 8,000 from our starting point of 1,000. So that's the idea for today. taking some of our pieces from the past of solving, putting them together with some old skills with compound interest, and that will help us to get some value. So as always, thanks for watching.